formations of galaxies and other cosmic phenomena which creates ripples in the space-time that are as huge as our galaxy requires the most impossible engineering challenge of making a detector with an arm length as big as our Milky Way galaxy. However, this engineering challenge is tackled beautifully by utilizing millisecond pulses, which are precise cosmic clocks, and using millisecond pulses and art as a to create a detector as big as a galaxy, and that method is called the pulsar timing array. So, pulsar timing array, as the name suggests, uses millisecond pulses, which have the period of milliseconds to nanoseconds, and by meticulously taking the readings of their time of arrivals, that is the beams emitted from the from the pulsar stars, and by meticulously taking the readings over the period of time by the ground-based radio telescope. This is the beautiful illustration of how PTA works. So whenever a gravitational wave sweeps across the galaxy, this affects all the pulses present around, causing the time of arrivals of their beams to be delayed or are leaded from their expected time. By taking the timing residuals and the correlations from pairs of pulses and their angular separations, PTA brings forward the correlation curve, and which is the Harings-Down correlation curve. In 2023 June, International Pulsar Timing Array, which comprises of 4 PTAs, one is Indian PTA Pulsar Timing Array, has stated to have the Harings-Down correlation curves in their data, which are these four graphs from the different PTAs, and they unfold the Harings-Down correlation curve is one of the most important curve for the suggesting the presence of a gravitational wave of low frequency in the background. As of now, in 2023, the collected data sets of PTAs shows 3.5 sigma, while Chinese pulsar timing stands at 4.6 sigma. Even though they are above the golden standard of astronomy, which is 3 sigma, they are striving to get for 5 sigma, and they will be continuing these research and collect more data to get a precise Harings-Down correlation curve. So PTA is a rising star, as it is facilitating the studies of supermassive black holes, then these formations of galaxies, then understanding the current gravitational theories, and most importantly will facilitate multi-messenger astronomy alongside electromagnetic EM observations, which are the telescopes we have now. So, and this one, as PTA has the potential and will be revolutionizing gravitational wave detection in a whole level that was never possible for the humankind before. So, these are the reference. 3 of these papers are from the PTAs recently, 2022-23, and these are the 3 of the pulsar timing arrays, official cases. From there, we took the data.
So this PTA will be probing the nanohertz frequencies, right?
Yes, sir, from the nanohertz.
So that can, you know, what would be the kind of wavelength that is
wavelength, like a rough estimation. Like the size of a galaxy, like light years. Like Milky Way has 1 million light years length.
Million
light year length. So the wavelengths will be above that size. So detection by LIGO and others are very important. So they need wavelength of such detectors to be as big as the galaxy, and this is done by using pulsars as a source of light to get.
So this is the main objective of this kind of work. You can probe, so you can probe very long wavelength from this kind of detection.
Yes,
that is definitely not possible.
Yes, sir. That is really not possible. It's an impossible engineering challenge. Impossible.
It's a natural detector.
Yes.
I just have a different question than this. So this is we are talking about very low frequencies of nanohertz and so on. What about high frequencies? As you said that LIGO can detect in hundreds of hertz or something.
Yes, 1 to 100 hertz.
It's sensitive to beyond 100 hertz for your information. It's usually given in 20 hours, I think something about kilohertz, but it usually don't detect kilohertz. But what about the high frequencies? Do you know about upcoming detectors which can detect both high
Ultra
energy?
high frequency.
Ultra energy and
Like recently, it will be one space-based interferometers will be LISA. LISA will be from NASA. It will be sent in 2035 maybe. I'm not sure that much. So LISA will be like the Earth-sized gravitational wave detectors that will use three space probe maybe three space probe to see the two will be lasers and to see if any gravitational wave passed it, if there is any change in their wavelength. That's the one of the space interferometer it will be. That's one of the I know about. So and LIGO, I think India is also having one LIGO for it. And
it will address the same sensitivity with the current LIGO detector. LISA will also be probing some low frequency.
Yes, something between Pulsar timing and LIGO. That's
Yeah. So, if you know that you can read about Cosmic Explorer and Einstein Telescope.
Einstein, yes.
So those will be detecting these gravitational waves at high frequencies. So you can read about that. That and really, it's a very nice talk and thank you very much.
So I wanted to ask one thing just for information. So, does this pulsar timing array even give you sky localization of from where the source of the gravitational wave is coming?
So what's
Sky localization.
From where the
sky localization? I think right now they are not able to because gravitational waves of like supermassive black holes are all like noise. As we can see, these noises we can't detect one from another. Like so, it's like that. So gravitationally, like background, this gravitational wave is in the background from very distant massive object. So they can detect it, but pinpointing the source is still difficult for PTS right now. They're developing something, I guess, for to pinpoint, but right now they are not. They are like able to see the surface of the ocean, like if there is a ripple or not of that wavelength. Like not the pinpoint of the source right now.
Even these observations can be from the very early stages of the universe.
Yes, sir. It can be from very
High redshift. If you have heard about redshift, so it's a look back into the past of the universe. You can read about that.
so you're from which
so I'm from Pandu College.
and just your grade?
I'm in the sixth semester right now, so astrophysics is just being introduced right now to us.
Okay. And fourth semester.
They haven't got right now astrophysics. They haven't got like just for pure interest. That's the reason we are just.
That's really great.
So who designed this post?
So I designed it. He also helped me with finding the pictures and all, and then have to think which one goes with which one. Those are done by me.
Who else?
So this he helped me to find pictures for all this one. We have collected many pictures, though some of them are not there. So after like analyzing what to put, what to not, that was done by me. So this poster design was me done. He helped in finding all these pictures and etc. and checking if the data what I got is correct or not.
This is the research part.
Yes, sir.
Okay, did you get any help from your professor or something?
So actually, right now we are exams, so we haven't got any like help from the teachers. This is like pure interest
So
of
as a
my
guide,
right. Like I have joined the previous competitions. There, teachers have taught me how to do and all. So I'm kind of on my own to see
this
how I
is on
do.
your own.
Yes, sir. So teachers have helped me before how to present, how to do, or how to make. So right now I'm just on my own testing whether I can do it or not.
Yeah.
Yes, sir. And the orbit, and it is also depend on the eccentricity of that orbit. Thank you, sir. Thank you, sir.